Awesome. Yeah, thanks heaps for the opportunity to speak, and I'm very sorry I can't attend in person. It's just been one of those days. What I'm going to talk about is very briefly about the effects of terrestrial runoff on the water clarity and on results in the Burdekin region of the Great Barrier Reef. So I'm really focusing on downstream areas like east of the Burdekin River mouth. I'm not talking about anything terrestrial. We all know the Burdekin River exports large amounts of sediments and nutrients into the GBR, and some state that those loads have increased about 5 pre-industrial times. Now, there has been a lot of controversy how much of the reefs are actually affected by the water quality issues. And the main focus of people often is on the plumes, which disappear quite quickly. So you get on the left-hand side here the Burdekin River discharging large amounts of sediments. They drop out very quickly indeed. Finer sediments are transported a longer distance and the nutrients retained in the system. Now the thing is that the Great Barrier Reef is on a shallow continental shelf. That means the sediments that are discharged are not just disappearing. They are staying in the system, they are being resuspended over and over again and continue to affect the marine communities. We really need to investigate water quality in the context not just of the places and the times when we can see the river plumes, but for the whole year, for the whole Great Barrier Reef. And that's what we've done. We've used satellite imagery to investigate really for every square kilometer, for every day over 10 years, the link between what comes down the Burdekin River and how clear is the water in the Great Barrier Reef. And if you summarize those very complex and big data, you can see that between 2011 with Cyclone Yasi was a very big year, 2006, 2004, 2003, they were all fairly dry years. So if you plot mean annual water clarity in the Burdekin region marine sector against how much fresh water came down the Burdekin River, you can see that the water clarity on an annual average, so not just after the plumes, but on an annual average, is 22% lower in the wet years compared to the dry years. Now that makes a difference between seeing the fish and being able to catch it, or not seeing the fish and not being able to catch it. Fresh water itself does not reduce water clarity, but it associated loads of sediments and nutrients that are contributing to reducing the loss in water clarity. So we're also getting the same plots. If you plot the loads against the load of phosphorus on the horizontal axis compared to mean annual water clarity on the vertical axis, the relationships are slightly different. They're particularly strong for the inshore and the lagoonal areas, and they're a fair bit weaker for the coastal areas and for the outer shelf. But overall, the relationship really shows that the whole sector of the Great Barrier Reef, inshore to offshore, is affected. The coastal areas a little bit less because they're chronically turbid and we see high turbidity most days of the year when the wind is blowing, and the relationship is also weaker further offshore because less of the mud is reaching the offshore areas. But really, the inshore, the lagoon, and the mid-shelf are all affected by this very strong relationship. Now, on a year where the discharges of sediments are high, the discharges of nutrients are high as well, so we can't attribute this loss in visibility to any particular fraction of runoff. We don't know whether it's the phosphorus or the nitrogen or the fine sediments. And overall, it's very likely that the combination of all of those materials is responsible for this loss in water clarity. Does it matter? If you ask the fish, they'll probably tell you yes. if you ask the corals, they definitely say yes. If you've got more turbid water, you do get more seaweed, you do get lower coral diversity because sensitive species are missing. The seagrasses and corals are restricted to shallow water, coral quite steep down the reef slopes. And if you get more sedimentation, you've got a very severe reduction in coral recruitment, and therefore a slower recovery of reefs after disturbances from bleaching or Renaissance starfish or cyclones and so on. So these are really, really strong relationships established by hundreds, literally hundreds of studies over time. There's no dispute, and it's not just restricted to inshore reefs. There are some offshore as well. But on the inshore, the effects through sedimentation is particularly important because we are concerned about coral recovery, and the limitation of reef growth and seagrass growth in shallow water is particularly important as well. So the way how it looks like is that if you see young corals, they are affected by the sedimentation. They basically get smothered, or they get overgrown by the algae, by the seaweed, and die. Whereas if you could grow juveniles in clear water, they can grow quite quickly. They grow more quickly, and so they are growing out of the size range where they are particularly vulnerable. We get a very strong relationship between the density, the number of young corals, and water clarity. On the offshore reefs, the effects on corals is a little bit more complicated. There's certainly not as severe effects, but what we're concerned is that, as I've shown you, there's less water clarity, that means less light. The direct effect of corals is likely severely reduced growth. We really have very few data on coral growth in the field. These are laboratory data. For example, here we exposed the corals to changing levels of light, and you can see the growth rate here per day in low light, medium light, and high light for a couple of species. And the growth rates really can drop by to less than half if the water clarity changes, as I've shown through the vertical changes. The last effect I want to talk about is the effects of the Burlington River floods and the outbreaks of coral-eating Carnosaurus starfish. Most of us are aware of these starfish that are contributing up to 40% of losses of coral on the Great Barrier Reef. And really, if you look at the annual discharges of the Burlington River here plotted over time through the water years, I've highlighted the years that had particularly high loads of fresh water and nutrients coming down. And lo and behold, these are exactly the years when Carnosaurus outbreak started. Not in the same year, but 2 or 3 years later, because outbreaks take a little while to develop. But the 1950 flood was followed by an outbreak in 1962. The 1974 flood was followed by an outbreak in 1978-ish. And same as 1991 flood was followed by an outbreak in 1994. And again, the very wet years 2008, 2009, and 2011 correlate with the re-emergence of Carnosaurus outbreaks that were observed from about 2011 onwards. So each year with big vertical floods have been followed by Carnosaurus outbreaks as long as enough corals were around. So there are mechanistic understandings and mechanistic explanations why that is. If you get high levels of nutrients, you get high levels of chlorophyll, and literally this is a real picture. There's no filter applied to the picture. On the right-hand side, it's in Burlington River. It's magnetic island in the time of flood. The water is very green. That means chlorophyll. The chlorophyll is nutrients for the little larvae of Carnosaurus starfish that are feeding on the algae. And on years with low chlorophyll and low microalgae, the Carnosaurus larvae starve. In years when the water is enriched with nutrients, they really proliferate and form new outbreaks. So this is a bit of a rocket. It runs through a very complex field of research and decades of research, really from hundreds of people. But overall, the real strong consensus is that the discharges of the Berghecken River strongly affect regional water clarity. If you reduce the nutrient sediments, that will measurably improve water clarity, and literally 1 year to the next, you can see years with lower loads of vertical discharges already have better water clarity. And we've got lots of studies and monitoring data that show that reducing river loads will lead to a significant ecosystem benefits for the Great Barrier Reef. Fewer macroalgae, fewer concerns starfish outbreaks, and higher coral diversity. And very importantly, at the time of climate change, quicker recovery times for the after disturbances.